Today we're talking about the next generation of robotics. Scientists have just created ultra-fast shape-shifting micro-robots called Rhagobots, inspired by ripple bugs. The bugs use a rapidly deployed fan-like structure attached to the end of their legs to propel themselves with extreme efficiency. Inspired by this, engineers designed a miniature robot just millimeters across, able to morph its structure almost instantly. This breakthrough could reshape the future, not just of robotics, but medicine, search and rescue, and even warfare? Let's dive in and see what physics is driving this revolution. I'm Ben, this is Physics or Bust. Not all robots are built to look like humans. The next generation of robots, especially micro-robots, might be built looking like bugs. Researchers studying Rhagobots water striders, sometimes known as ripple bugs, tiny insects measuring only 3 millimeters long that skim across the water's surface, noticed something remarkable. These little bugs were highly efficient in their very rapid movements and could keep moving rapidly for far longer than expected, which meant that these bugs had a way to move across the water using less energy than researchers expected. We'll dig into the physics in a minute, but first, if you like this video, you'd probably like this book. I've got a link in the description below. I do get a small commission, but it wouldn't cost you any extra. The key to their efficiency is at the end of their middle legs, which they use for propulsion. If the middle appendages are out of water, they look streamlined and aerodynamic. But the moment they touch water, something remarkable happens. Surface tension triggers their fan-like appendages to deploy outward, almost like a blooming flower, giving those bugs a big oar for moving about. So what did researchers actually build? Meet the Rhagobot, a millimeter-scale robot inspired by ripple bugs. These Rhagobots don't need motors or bulky actuators to deploy their fan-like structures. Instead, the mechanism for the deployment is about geometry and structural stability. Think of a piece of paper. If you pinch it at just one point, it flops around easily. But if you hold it at 3 points and curve it slightly, suddenly it becomes rigid and holds its shape. The Rhagobot uses the same principle, structural reconfiguration, to switch between flexibility and rigidity. The result? Robots that can reconfigure themselves hundreds of times faster than previous micro-robot designs. When surface tension pulls on certain contact points, the robot's thin structures snap into a new, rigid, expanded configuration. Pull it back out of the water, and the fans collapse, returning to the streamlined state. It's a reversible, natural switch powered entirely by the physics of surface tension and geometry. That's what makes it such a breakthrough. At tiny scales, motors and gears become impractical, but physics itself can do the heavy lifting. So why does this matter? Let's zoom out. One of the biggest roadblocks in micro-robotics is that physics doesn't always scale nicely. When you shrink a system down, forces don't behave the way we're used to. For example, at the microscale, surface tension dominates over gravity. Friction and drag become overwhelming compared to inertia, and batteries or motors, things that work fine in your phone or car, become absurdly inefficient when miniaturized. Traditional robots can't simply be scaled down. Their moving parts, gears, and electronics stop working efficiently, like trying to run a jet engine inside a grain of rice. Newsflash, it's not going to work. That's why Rhagobots are so important. Instead of relying on scaled-down motors, they use natural physics. The result? Movements that are not only much faster, but also require far less energy. It's a fundamental rethink of robotics. Instead of fighting the physics of the small scale, this design embraces it. And that opens the door for machines that can thrive in environments where traditional robots simply fail. So what could this mean for the future? The Rhagobot may only be a proof of concept today, but the underlying physics could unlock huge possibilities. In medicine, a scaled-down version could one day travel through the bloodstream. While that's still far off, the concept is compelling. Robots that can shift between streamlined travel mode and expanded anchoring mode, perhaps for delivering drugs precisely where needed, or temporarily attaching to tissues for microsurgery. Now here's an important detail. The current Rhagobot design works because it uses surface tension at a liquid-air boundary. Inside the bloodstream, that trick won't work. The physics is completely different. Blood is not only thicker than water, but there's also no open surface for tension forces to act on. But the breakthrough here isn't just about surface tension. It's about the bigger principle, harnessing physics and material geometry to drive fast, controllable shape changes. That principle could be adapted into designs that work in viscous fluids like blood, by using other triggers, chemical signals, magnetic fields, or even localized heat. And scaling this concept up, we have the material science angle. By studying how structural geometry can be harnessed, engineers may be able to design larger-scale deployable structures, satellite solar panels that unfold without motors, drones that shift wing shapes mid-flight, or even buildings with shape-shifting elements that adapt to wind and earthquakes. More closely at hand, there's the idea of micro-robot swarms. Imagine thousands of these tiny machines released into an environment. In civilian applications, they could be used for environmental monitoring, skimming across lakes to detect pollutant sources, or they could be used for search and rescue, fanning out across flooded areas and disaster zones to relay sensor data so that emergency personnel know where people that need their help are located. But swarms also raise in my mind the idea of military possibilities. Picture a wave of Rhagobot-inspired robots deployed for search and destroy operations. They could speed across water surfaces, spread out into wide formations to detect enemy positions, attach themselves to the enemy, and then send out signals to be located. Swarms of thousands could be deployed, operating semi-independently using their physics-driven design to increase their range and effectiveness. What I love about the Rhagobot is that the breakthrough isn't about complex electronics, heavy motors, or expensive batteries. It's about physics itself. Surface tension and geometry working together in a way that looks almost alive. It's a blueprint for physics-first engineering. Machines that work with natural forces rather than fighting against them. These robots are directly inspired by ripple bugs, but the approach can extend to countless biological systems. Engineers could scan the natural world for efficient, physics-driven movements, then translate those into machines. In a sense, nature becomes the blueprint for the next generation of robotics. If history is any guide, this kind of physics-first engineering often leads to revolutions. Think about the airplane wing. Once we understood lift, flight became inevitable. Or the transistor. Once we understood how electrons move in semiconductors, the entire digital age was born. Rhagobots could be the first step in a similar transformation for robotics. Right now, it's just a lab prototype, but the ideas behind it, physics-driven design, geometry, mechanics, and swarm potential, could ripple outward into robotics, medicine, space engineering, and even military strategy. Where do you see the descendants of Rhagobots being used? Let me know in the comments below. If you enjoyed this dive into the newest micro-robots, remember to like and subscribe, and remember, keep asking questions. I'll see you on the next video.